Welcome everyone to the first lecture uh, in this course, Advanced Mechanics of Solids. In this lecture, we will see why this course is important and why we should study the content in this course. So we'll start off with simple things, reviving what we know based on our day-to-day observations, as well as what we have learned in Strength of Materials course. And then we will see why this course is important, or rather why the concepts presented in this course have relevance to mechanical engineers. So if you look at mechanical engineering from a distance, what comes to mind is the design and development of various kinds of engineering systems. It could be various kinds of machines, starting from pumps, turbines, wheels, chairs, tables, machine tools, automobiles, okay, and to the current day robotics, right? And further, each of these machine has its own function. And by function, it can have various kinds of things. For example, if you consider a wire, an electric wire, when it is fabricated, it is drawn through a series of wires where there is severe plastic deformation, and eventually you get a wire, metallic wire of desired cross section. And then a bunch of wires are stranded, and over which a particular coating, a particular electrical insulation coating is being laid on. Now that involves two kinds of physics. One, the wire needs to conduct electricity. Second, due to the motion of electrons in the wire, it gets heated up due to Joule's heating effect. And the electrical insulation coating, whichever is being laid on the wire, also has now two purposes. One is it must do its electrical insulating characteristics. That's what it must exhibit. And the second thing is it must also not let the heat dissipate to the surroundings. So it has to be both electrically as well as thermally conductive. So what are all the physics that we have encountered? There's electrical engineering in it, there's heat transfer, and there's solid mechanics at the same time, because you don't want the wires to be stressed out, because that would lead to plasticity and eventually local deformation. So like that, so just by analyzing a wire, we could see that there is electrical engineering, heat transfer, solid mechanics, and a bit of thermal engineering. Likewise, each of any of the engineering system you pick will have a series of functions involving various fields. It could be heat transfer, mass transfer, fluid flow. And most often these days, it is all mostly interdisciplinary, but still solid mechanics does play its role in addition to other disciplines. So broadly, when engineers design and develop machines or instruments, or broadly engineering systems, each entity has its function. Okay. And in that, always, most often, you don't want the structures to buckle or fail, or you don't want them to be broken, or you don't want to see a mechanical failure. And that's where this course comes in. Okay. So solid mechanics basically comes there. This stability, the structure, the stiffness, okay, and its ability not to fail or fracture. Okay. And when we say a machine, it's not just one entity, right? Wire, we picked up one of the simplest example. It's just a two-layered, two medium material, two medium structure. One is a wire, outside, external to it is the coating. But in general, a machine comprises of various modules or components, and in each component, you will have this various functions which need to be catered to. And all these functions, all these components are subjected to either forces or displacement, regardless of whether it is intended to take loads or not. For example, if you consider the case of the electrical wire again, there it was not intended to take any mechanical load. Usually it is clamped to its surroundings. It is not intended to take a mechanical load. But at the same time, due to the heat flow in it, there will be thermal expansion and there will be thermal stresses. So even there, although the primary function is to make sure electricity passes through and the heat is being dissipated just locally and it is not dissipated to the surroundings, there is still solid mechanics involved because you don't want the thermal stresses in the metal to be so high that the plastic cladding around it begins to rupture. Right, so there is still a bit of solid mechanics even there, even in the simplest of the engineering systems. Likewise, if you consider any component or subcomponent or submodule of any of the larger entities that you look around, there is solid mechanics involved, mainly primarily involving forces or displacements, or for that matter, the thermal stresses, the changes due to temperature. So these are the main aspects in which we will analyze any structure with, whether we analyze a disc or a gasket or a pressure vessel or a beam or a truss. We will look at it, we will try to look at it with respect to the perspective on what is the forces and displacement that it undergoes, or what are the corresponding changes that one needs to take note of. So stress, as you have already defined formally in the strength of materials course, it is a second order tensor. We will also again define the Cauchy stress. But if one has to evaluate the component of a stress, it is the resistance of the object to the applied force. It is not external force divided by the corresponding area. It is resistance to the applied force. For example, if you consider a balloon, so let me pull out the drawing pen. Yeah. So if you consider a balloon which is resting on a surface, and you put one more plate on top of it, right, and you start to apply the load, the stress due to the externally applied force, the pressure inside also will change. Right, the pressure in the material deforms, and due to that the internal pressure also changes, and the stresses, the local stresses will also change. So the effective stress here is not just external force divided by area. You know, you'll have to account for the change in pressure, and based on that you evaluate the hoof stress, and that's how you evaluate the stress. So stress is not always force over area. It is the resistance of the object to the applied force. So this is one such example where you account for the pressure changes, and accordingly you identify the hoof stress. Or if there is no symmetry, the corresponding other components of the remaining components of the stress. So stress is the resistance of the object to the applied force. It is not just force divided by area. Most often we do not encounter the situation which I have drawn here, but it is always helpful if we keep an eye open to what the actual free body diagram is. Well, let me clear the drawings. Right. So from a design engineer's perspective or a mechanical engineering engineer's perspective, why should we even evaluate the stresses? It's basically to see whether the corresponding value of stress or strain is below a particular level, and you should be able to tell how much of its life is remaining. Okay, it is not like a entity runs perpetually forever. It is not, even despite external supply of external energies, that any object has a particular life, and we should be in a position to identify objects or a part's remaining life. That we will see more of it in ME 351 course, where you would be predicting what is the remaining life of a particular component. So let us start by reviewing what we know in strength of materials and what this course offers in addition to what strength of materials has taught us. Okay, so we'll start with one of the basic things, also called as bar under tension or axially loaded bar. Okay, for now the cross section of this bar, two-dimensional bar, is uniform, and I'm applying a load P with its initial length L0 as shown. Now you know by now that as you apply load axially to a bar, it elongates, and simultaneously the cross section also decreases. So the slenderness ratio basically increases under tension, right? So, and what do we know? We can calculate the uniaxial stress or the normal stress and the corresponding normal strain, right? However, this is not entirely true. It became possible due to the following things. We made a few assumptions. The first is that object is in equilibrium, which is fine, which is a fair assumption. And here in particular, we are considering the object to be at static equilibrium. And this is a important assumption, which we will relax when in this particular course. The assumption is this: when doing strength of materials course, we have considered that the stress and strain are uniform across any cross section. If I look at any cross section, as in if I draw a line here, or rather here, and see along this cross section, at any point the stresses are the same, which was sort of fine for slender objects, but not otherwise. Okay, and the stresses the stress and strain are the same at every point. Whatever strain I have at this point is the same as this point, is the same as this point, here. Essentially, this object is treated as a point. In writing these two, taking care of these two assumptions, assumption 2 and 3, we have idealized the object as a point, which is not always desirable. So in 321, in this course, we will relax these assumptions. We will try to solve boundary value problems and write the stress tensor as a function of position, and also the strain tensor as a function of position. This is what we will do. So there's a limitation. It's not like a limitation, but it's a kind of, it's more to do with the scope of the course that we ended up using these particular assumptions. Likewise, if you consider the bending of a beam, the beam theory which you guys used most likely was Euler-Bernoulli beam bending theory. And in that, you defined a neutral axis based on where the axial stress component was 0. And depending upon whether it is in, that upper part is in compression and the lower half is in tension. So accordingly, you define the strain and the stress. And of course, again, uniaxial. There is no other component of stress or strain here. And rho and E are the Young's are the radius of curvature and Young's modulus. But key is this: even here we did make certain assumptions, which may be fair for, again, long enough structures, slender structures. Okay, and that cross sections remain plane during bending. Or cross sections which are plane before deformation will continue to remain plane after deformation. That was one assumption. And that there exists a neutral axis always where the strain is 0. And the curvature, this is something more important. The curvature is small. Normally, the radius of curvature is 1 plus dy by dx whole square power 3 by 2 by d square y by dx square. So we have said dy by dx is small, and hence this term only always factored in our weight distributions everywhere, in analyzing the moment distribution as well as the shear force distribution. So dy by dx was always small. So you cannot take a wire which is sitting next to your computer. It could be the wire of your mouse or the headphone. You can't say that you will use Euler-Bernoulli beam bending theory, although the structure is still slender. In fact, it is more slender than, it has a slender ratio which is much higher than most of the engineering structures that we consider. So this is again a key issue, that not always do the curvatures have to be small, is an assumption that needs to be relaxed. So this was one more limitation of strength of materials course. Of course, I thought I'll just give you a quick recap of how we derived the moment. Basically, you took a particular cross section, you balanced out the moments, and you equated it, you recast that moment in terms of moment of inertia, and then you have your flexure formula. Right? So this is the theory in some 2 slides. So you may want to revisit your Euler-Bernoulli beam bending theory before you begin from lecture 2 onwards. And you can see the other courses other concepts that you have studied. You can start with torsion, for example. We have seen 2 things: uniaxial loading beam bending, torsion is again one thing, and a thin cylinder subjected to internal pressure. If the cylinder has a density which is dependent on position, or Young's modulus dependent on position, then such a straightforward theory of strength of materials cannot be directly used. Okay, and often a material is not just a structure is usually not comprising of one material. It involves a series of materials. For example, if you have a composite cylinder, this is a composite with wirings on one side, and this could be the internal one can have the windings in the other side. Okay, and they could be glued together with another kind of medium. So this is actually a kind of functionally graded material, or two different kinds of materials. Sometimes it is possible that you may want to vary the density with distance. So depending upon what kind of material we need. So the limitations exist due in the concepts learned in strength of materials to solve advanced problems, or problems which are more closer to reality. This course basically tackles those issues. Things which were unresolved in strength of materials course will be resolved in this particular course to a reasonable extent. Of course, we will not be able to solve entire thing. As for example, can we be able to analyze a chewing gum? A chewing gum is when you purchase it, it's in the kind of a cuboid, and eventually it does get deformed into various shapes. That's very large deformation. That actually comes under very large deformation, and there you cannot use ME 321 concepts as well. That comes as a slightly higher order theory, large nonlinear deformation. In this course, we will not get to that stage, but we will lay the foundation such that you would be in a position to analyze most problems. At least you will be able to formulate. If not analytically, you would be able to proceed towards your solution numerically. That is where we will lay the foundation with. So the first, so this course, as you know, has lab and lecture. The first half, we will formulate. Mostly the first half of the course lectures part will all be formulations, and the second half will be on solving two-dimensional and three-dimensional problems. So if we scroll back a couple of slides and see the axial loading of a bar and beam bending or even torsion, these are all one-dimensional. I mean, we have essentially solved the problem in a one-dimensional way. So this course, ME 321, we will solve problems in 2 dimensions. And if time permitting, we will solve even 3-dimensional problems. All right. So that is the essence of this course. And further, as the parts get complicated, you cannot always do one-dimensional analysis. You cannot really do one-dimensional analysis of stress or strain. You would need to do a full field approach, for which this course, the Advanced Mechanics of Solids, or also called widely as the Theory of Elasticity, the concepts in this course are used. But can we always have an analytical solution? No. For example, if you look at the shape of a turbine, it is not a simpler shape. Towards one end, the thickness is larger, and towards the other end, the thickness is small. Right, and the thickness varies both in the radial direction as well as in the axial direction. So analytical solutions for these kinds can be approximated as a wedge, and you can also even solve this kind of structure by using what is called as a superposition principle. But not always, not every complicated shape can have analytical solutions, and that's the reason we must realize that complex shapes often do not have analytical solutions. We will be able to pose the problem and we may end up solving it numerically. Further, these days, you look at robotics, the current generation of robotics research is mostly to do with soft materials. The traditional robots are all hard materials with iron and then motors and strings and pulleys. That's the past generation of robots, but the current generation of robots employ what are called as artificial muscles. So even for those, to analyze those, you would need strength of materials concept. Bamboo is a very good structure, good structurally. Okay, And even if you have to analyze any biological sample, it could be human tissue or it could be plant tissue, all of them would require concepts that you would learn in this course. The concepts that you learn in this course are not just sufficient to analyze everything that you see on this slide, but they are the next step towards analyzing the remaining things. Okay, so various kinds of artificial structures called metamaterials. Even for those, the bottom figure which you are seeing here, this hexagon and the negative Poisson ratio kind of structure, this kind of structures are called as metamaterials. And for us to analyze these kinds of structures which have characteristics different from naturally occurring materials, the analysis required, the concepts required are essentially those which are learned in 321. Okay, so it is not just limited to our course and exams, but to the more diversifying and intertwined branches of mechanics as well. Okay, so in summary, strength of materials does work for homogeneous materials and for simple kinds of loads, and you do work with simpler shapes. And in most cases, you know, when I write cases where deformations and stresses can be guessed, we know upfront what is the only non-zero component of stress or strain. You upfront know by looking at the body and by analyzing the free body diagram. And so this strength of materials does solve a huge portion of the problems which are used in engineering services, but advanced problems will not be able to solve using purely the concepts in strength of materials. We would be, of course, banking on these concepts to build higher order theories. And again, too many assumptions from reality, small deformations, plane sections remain plane, and so on. The list goes on. And three-dimensional state of stress and strain cannot be accounted for in strength of materials course. So that is the reason we are doing this course. And in this course, we will primarily be using partial differential equations towards solving stresses, strains, and displacements. So the objectives of this course is this. It is to develop a general formulation for stress or displacement analysis of any arbitrary shaped linear elastic body. We will worry about, or rather we will be concerned only with linear behavior. For example, what is linear behavior? Sigma is Young's modulus times epsilon is linear behavior. If I have to make this non-linear, sigma is E times epsilon times 1 plus beta times epsilon. This is a model which is often used in this area called as nonlinear ultrasonics, where beta is the nonlinear parameter. But this has a huge significance. This nonlinear parameter will tell us whether a material has accumulated any damage or not. The area is called as NDE, non-destructive evaluation, NDE. In that, you may want to look at ultrasonics, those of you who are interested in. It is nonlinear ultrasonics. You know, identifying this parameter is of huge importance to all the design engineers who would want to say, okay, whether a gas line is going to break or whether a structure is going to fail in a particular amount of time or not. So, however, we will restrict ourselves to linear cases. So we will do general formulations. Wherever possible, we will try to do analytical solutions. Wherever it is not possible, you may want to try an advanced technique such as a boundary element method or a finite element method. And how are we going to do it? Mathematics remains our tool for solving, for going through these lectures. We will be using lots of partial differential equations. Those of you who would want, who are not really good with mathematics, I suggest you have a standard engineering mathematics textbook such as that by Erwin Kreyszig. So we will be using all partial differential equations. Okay. These are some references. One is an NPTEL source, and this particular reference, the second one from New Zealand, this particular web page has about 5 books, one of which is useful for us, and the remaining 4 are for advanced mechanics. Even further, like nonlinear deformation, fracture, and so on. But this is free for academic purposes. Okay, so you may want to have a look at them. All right then. So from next lecture onwards, we will start with the definitions as to what is displacement, how do we go about defining it, and then we will define, instead of writing long equations which run into various pages, we will look up this indicial notation or a short form notation, and we will begin from there. All right. So I'll see you guys in the next lecture.